Welcome back to the deep dive. Today we are tackling what is probably the most famous challenge in all of combinatorial optimization,
The traveling salesman problem.
the TSP. Exactly. It sounds so simple on the surface. You just find the shortest possible route that connects a set of cities, you visit each one exactly once, and then you return home.
But that simplicity is, well, it's incredibly deceptive.
It really is.
The general version of this problem is the textbook definition of NP-hard.
And what that means is that the time it takes to find the absolute best, most optimal tour, it just scales catastrophically.
Oh, completely.
Ah.
For, even just a few hundred cities, the world's fastest supercomputers would take longer than the age of the universe to check every single possibility.
That's overwhelming. So finding the absolute perfect path is basically impossible.
In most practical cases, yes.
But we aren't chasing the impossible today. We're focusing on a specific version that gives us a really important shortcut, the metric TSP.
Right.
So what changes when we add that metric constraint?
The metric part just means the distances have to satisfy the triangle inequality. So think of it like this. The direct path from city A to city C has to be shorter than or equal to going from A to B and then from B to C.
So no weird wormholes. You can't cheat the distance by taking some bizarre indirect route.
Exactly. And that constraint, it seems simple, but it's critical. It gets rid of all these weird edge cases, and most importantly, it opens the door for these really powerful approximation algorithms
So we can stop looking for absolute perfection.
and start guaranteeing results that are provably good.
And that brings us right to the core of this deep dive. We're looking at a hybrid solution that combines two totally different ways of thinking.
We have what we're calling the architect and the craftsman.
Right. Christofides' algorithm is our architect. It provides this incredible structural guarantee.
And then you have the two-opt heuristic, which is our craftsman. It comes in after and does all the meticulous refinement.
Our mission here is to show you how this partnership really works. The architect lays down this robust, theoretically sound foundation.
And the craftsman comes in to apply the polish, making the route practical, efficient, something you can actually use.
By the time we're done, you'll see how this combined strategy gives you a path that is both theoretically bounded and locally optimized. Okay, so let's start with the architect, with Christofides' algorithm.
Mhm.
With an NP-hard problem, you have to fundamentally shift your goal, right? You're no longer looking for that perfect 1 in a quintillion optimal path.
You're just not. You have to look for something that's guaranteed to be close to it. That's the key shift.
So what's the big achievement of the architect then?
It's not a perfect path. Its greatest achievement is a reliable guarantee.
The approximation ratio.
The approximation ratio of 3/2, the famous 382/2. That ratio is, well, it's the algorithm's signature strength.
Okay, so break that down. What does 3222 actually mean for you, the listener, trying to solve this problem?
It's a guaranteed ceiling on how wrong you can be. So let's say the cost of the absolute best possible tour, the one we can't find, is 100 miles. Christofides guarantees that the tour it generates will be no more than 1.5 times that. So 150 miles or less. It cannot be worse than that.
So you're basically accepting up front a potential 50% penalty over the perfect route just to get a solution you can actually compute.
Yes, it's a powerful trade-off. It's risk management. This theoretical bound is what separates a proper algorithm like this from just a simple guess.
You know the worst case scenario.
You do. And the power of that guarantee comes from its core components. It's a combination of a minimum spanning tree and something called a minimum weight perfect matching.
Why are those two things so essential?
Well, the minimum spanning tree, or MST, that gives us a lower bound. A spanning tree connects all the cities, but it isn't a full loop.
So it has to be shorter than any full tour.
Exactly. Logically, the optimal TSP tour must always be at least as long as the MST. So by finding the MST first, we establish the cheapest possible way to connect everything. That's our anchor.
Okay, so the MST is the bare bones structural minimum. And the goal of Christofides is to add just enough back onto that structure to make it a complete traversable loop.
Precisely.
Mm.
And to do that, it follows this very systematic 5-step blueprint.
All right, the architect is ready to build. Step 1, you lay that foundation, the minimum spanning tree.
Right. As we said, it connects all the nodes with the absolute minimum total edge weight. You get that cheap initial connectivity.
Then step 2, we have to inspect that foundation.
We do. We look at the MST we just built, and we find all the cities, the vertices, that have an odd number of connections, an odd degree.
We call those the odd degree vertices, or VIGDN.
Mhm.
So why are these odd degree cities suddenly so important?
Because for us to eventually trace a single continuous loop where we're aiming for, every single city must have an even number of connections. You need an entry and an exit.
That makes sense. It's a fundamental requirement.
It is. And here's the neat mathematical trick.
Mm.
Any tree, including our MST, is guaranteed to have an even number of these odd degree vertices. They always come in pairs.
That is very convenient. So that brings us to step 3, where we fix the oddness problem.
Yes, we introduce the minimum weight perfect matching. This is the really genius move. We take only those odd degree cities we just identified, and we find the absolute cheapest way to connect them into pairs, adding new edges to our graph.
So you're basically building little bridges between the cities that only had, say, 1 or 3 connections before.
That's a great way to put it.
Yeah.
And when you add these new bridge edges to the existing MST,
Every single node in the entire graph suddenly has an even degree.
every single one, we've just transformed our sparse tree structure into what's called an Eulerian multigraph.
And now we're at step 4, which is possible only because of that even degree property.
The Eulerian circuit.
Right.
Because every vertex has an even number of roads leading in and out. We are now guaranteed to find a path that travels along every single edge we've constructed.
The original MST edges and the new matching edges.
Exactly once. And it returns right back to where it started. A perfect loop that covers every inch of the structure we built.
Okay, that sounds great. But as a salesman, I don't want to visit the same city twice. The Eulerian circuit might be too long, right? It might double back on itself.
And it often does. Which brings us to the final and maybe most crucial phase. Step 5, shortcutting.
Okay.
We take that long Eulerian circuit, and every time the path revisits a city it's already been to, we just skip it. We create a shortcut directly to the next unvisited city in the sequence.
And this is where that metric TSP rule comes back into play. The triangle inequality.
This is the only reason this works. Since we're in a metric space, the direct path, the shortcut, is guaranteed to be shorter than or equal to the roundabout path we just cut out.
You never make the tour longer by shortcutting.
Never. And with that, you transform the long edge-tracing Eulerian circuit into a clean, simple Hamiltonian cycle.
The required TSP path. Every city visited exactly once. That's the whole architecture. It's sound, it's mathematically guaranteed, and you've got that 3-on-2 two-doll safety net.
But, and this is a big but, here's where we have to talk about the architect's biggest practical flaw.
Okay.
The structural guarantee is fantastic, but the actual path that you get from that shortcutting phase, it's often a real mess.
So we have a brilliant plan, but a tangled result.
That's a perfect way to describe it. Visually, the path is often just really inefficient. The shortcuts create all these lines that cross over themselves.
I can picture it. So for a delivery service, the algorithm guarantees you won't drive more than 50% extra, but your driver is constantly crossing their own path, making weird turns. The route just looks chaotic.
Exactly. The pure theoretical solution, it just lacks the finesse you need for real-world movement.
So the architect gives us this robust, if maybe a bit clumsy, foundation.
And now we need someone who specializes in refinement, in polishing.
We need the craftsman.
We need the craftsman.
Yeah.
The two-opt heuristic. The craftsman is a local search specialist. It could not care less about the global $3,222 guarantee. Its only job is to meticulously refine the path that it's given, cleaning up those ugly crossings until the road is as smooth as possible.
Okay, so the craftsman's main tool, 2-opt, is based on a really simple idea. The swap. How does this local swap manage to untangle the whole path?
It's an iterative process. The craftsman looks at the path and picks 2 edges that aren't connected. Let's say the edge from city A to B and another one from city C to D.
Okay, 2 separate segments of the tour.
Right. It then just checks what would happen if it swapped the connections. So instead of A to B and C to D, it tries connecting A to C and B to D.
I see. And if the original 2 edges were crossing each other, like an X, this swap would immediately uncross them.
That's exactly what it does. It calculates the new total path length. If the path gets shorter after the swap, it keeps the change. The path is now instantly better and less tangled.
And if it gets longer,
It rejects the swap. It reverts back and moves on to check the next pair of edges.
this sounds way less complicated than Christofides' 5 steps. It feels more like brute force refinement.
It is. And that leads us to the really critical performance differences between our architect and our craftsman. Let's talk complexity. The architect, Christofides, has to do that very difficult minimum weight perfect matching.
Which makes its complexity dollars and dollars.
Right. Right. So the calculation time scales cubically with the number of cities. If you double the cities, the time goes up by 8 times. It gets slow, fast,
Yeah, 1,000 cities is a billion operations. That's costly.
very. It's slow, but remember, it's what gives us that essential global guarantee. Now, the Craftsman 2-opt is much faster per pass.
How much faster?
It's $1 and $2 per pass because it's just checking pairs of edges, double the cities, and it only takes 4 times as long per pass. That's a huge speed up.
So we've got the slow but reliable architect setting the stage, and then the fast, repetitive craftsman doing all the cleanup work.
That's the perfect division of labor. Think about it. If we only use the Craftsman, 2-opts could get stuck. It might find a great local optimum, but from a terrible starting point.
So the final path could still be 10 times longer than the true best path.
Exactly. Because it's only focused on local improvements, not the big picture. By starting with Christofides, we guarantee that the 2-opt refinement process begins from a path that's already within that 3-2-2 boundary.
We're preventing it from getting trapped in a bad neighborhood, so to speak.
We are. It takes that rough, tangled path from the architect and just iterates, usually with a simple while-improved loop in the code, checking every pair until not a single swap can make the path any shorter. And at that point, we've found our local optimum.
And the visual change is it's the most striking part. You run the complex algorithm for the guarantee, then run the simple 2-opt over it, and the route just instantly unknots itself. It becomes smooth, efficient, ready to go.
And that synthesis right there, that's the key takeaway for you. This hybrid approach gets you a solution that combines the absolute best of both worlds.
It's theoretically bounded thanks to the architect's structural integrity and that 300-2 ratio.
And it's also locally optimized, thanks to the craftsman's iterative polish.
This idea goes so far beyond just math problems. If you're optimizing a supply chain, planning deliveries, even designing circuit boards, you need this exact balance.
You do. You need that structural integrity, knowing the worst case time or cost you're committing to, and you need the quantitative polish to make the route feel efficient for the person or the machine executing it.
The lesson here seems to be that for these really hard, complex problems, the solution isn't always one perfect tool.
It's a sequence of specialized tools. You start with the mathematically rigorous, maybe more costly foundation, and then you apply the faster, simpler, more practical refinement on top of it.
We often think of solutions as being either, theoretically perfect or practically fast.
But the architect and the craftsman proved that the best strategy is often to use the theoretical guarantee as a high-quality starting point for that practical, iterative refinement.
So as you face your own complex challenges, logistical or otherwise, maybe ask yourself this. Is it better to keep chasing that theoretical 100% perfect solution that you might never reach?
Or is it wiser to first use an architecturally sound method to quickly lock in a guaranteed good enough solution and then rely on a craftsman-like process to polish it into something that's elegant, practical, and finished? That's something to optimize in your own mind until the next deep dive.